Eike will ask how provably secure are cryptographic primitives used in practice?
Okay, yeah. How provably secure are cryptographic primitives used in practice? Okay, it's maybe a valid question to ask. So I'm a theory guy, so the daily life of a theory researcher can consist of, I mean, that's what I'm doing as a research job. I'm inventing new cool stuff that could be maybe predicate encryption. I don't work on that, but other theory people work on predicate encryption, I heard. Definitions are a hot topic. Leakage could be your favorite topic. You could work on the new NISIC or whatever you want. Or another thing that I like to do as a theory researcher in crypto, you could just look at things that are actually used in practice, primitives that are used in practice, more or less. And then look at that security. And the interesting observation here is that most of the schemes or the crypto used in practice are actually invented in the early 90s. And now we are in 2012, which is, some decades later. And maybe we have gained some knowledge, and maybe you can say something more about their security. Maybe they're more secure or less secure than you thought. Most of the schemes were invented in the so-called random oracle model. Maybe you can say something about the standard model security. Maybe you get a tighter proof, or with a spectral something like that. These are the questions that I like to ask. And this is what the talk is going to be about today. What? Okay, so today we look at a specific cryptographic primitive. I'm only going to focus today on RSA full domain hash signatures. Okay. In the booklet, you may can see that I also thought about talking about OAP and some other stuff, but I thought maybe I just focus on RSA full domain hash signatures and see how secure are they in practice. And the talk consists of two parts. The first is I consider security of RSA full domain hash signatures in the random oracle model, and the second part, which I don't know how much time we'll have. I think I will have some time. I will consider security in the standard model and see what we can say about that. So two parts. And I could, as I said, I could take a different talk about, each will be a 1 hour talk or even longer about maybe OAP. You can say similar things about OAP, these signatures, SSL, TLS. I wouldn't be able to talk about it. Maybe other people can talk about it. But, many people are working on this topic, which is nice because I find it interesting. Okay, so, what is provable security? So the 4 pillars of provable security as I call them, I like to call them. All right, the first step, the 4 steps. In the first step, you define a security model in some setting, and a security model that hopefully depicts reality. In a second step, you would describe a scheme somehow, right? Yes, PPT algorithms and all these things. You describe the input-output behavior, and then you sort of define and hopefully analyze some hard problem. Cryptographic hard problem should be a simple problem, non-interactive. Okay. And that should be a really hard problem, like factoring is a good example, or maybe discrete log or whatever you want. And the 4th step and last step, you do a security reduction from the security of the scheme to the hard problem. Okay, so that's what we do. Okay, so if you put all 1 to 4 together, then the scheme is, so then interpretation is that the scheme is actually secure. Okay, or of course in brackets, unless the problem is easy, the problem you find in 3. Or the model doesn't really depict reality. Okay, 1 to 4 happens. But okay, so that's then we made some other mistake. Okay, that's what we do. Okay, our example: RSA full domain hash signatures. So the security model is unforgeability against chosen message attacks. Goldwasser, Kali. All right. The scheme that we're looking at is second is RSA full domain hash. The hard problem that we consider is the RSA problem, and the 4th thing that what I'm going to do later, going to show you later, is the security reduction from unforgeability against chosen message, from security of the RSA full domain scheme to breaking the RSA assumption.
Where on the slide would be the random oracle if you see it?
That's a good question. It's in the model, I guess. Yeah, it would be in the model. Okay. Right, here it comes. So that's the security model that we're going to look at. And first we consider security of a signature scheme in the random marker model. And now we're going to look at concrete security. So I define that a security scheme is TF, so forger, F is forger, TF is the time that the forger takes, epsilon F is success probability, QS is number of signing queries, and QH is number of hash queries that he makes. Okay, so it's TF, epsilon F, QS, QH secure in the random marker model. If for all forgers running in time of most T, F, making at most QS signatures, and QH random marker queries, the probability that the forger wins is bounded by epsilon F. Okay, that's the concrete security definition. And if you want, here is a picture. I think I forgot the random marker queries. Okay, so the first, I mean, that's the game, right? The first public key is sent from the experiment to the adversary. Then the adversary can make a couple of signing queries. He can also make a couple of random marker queries. Can make at maximal QS signing queries and QH random marker queries. And then the end, he sends a message and together with a signature, and he wins the experiment if the verification procedure outputs 1. So this is the valid signature, and the message was not part of the queries to the signing oracle. Right? So that's all the standard security definition of unforgeable against chosen message attack. And here everybody knows what a random oracle is, so I don't have to explain it here. Okay, second pillar, now I describe the scheme. So the scheme I'm going to be looking at is RSA full domain hash by Belaga-Roggevei, proposed by Belaga-Roggevei in the year 96. All right, so a signature scheme consists of key generation, a signing, and a verification algorithm. So key generation works as follows. So we pick a random, we pick a public key and consists of an RSA modulus, n equals PQ, product of two random primes, an E, and public exponent should be co-prime to phi of n fully, and a hash function somehow, right? Magically it appears, it takes bit strings as input and it outputs a value in Zn. The secret key is the secret exponent. Its d is 1 to the e to the minus 1 modulo the order which is phi of n. Okay, to sign a message, which is a k-bit string, what do we do? So we first hash the message. So the hash function is a full domain hash. It hashes to the full domain. So it takes an it outputs here a Zn value and raises it to the 1 over e. Applies the secret exponent to it. Okay. So it inverts the chapter RSA chapter permutation on hash of n. To verify, we do the opposite. The signature s, we raise it to the e and verify if that is h to the m or not. Okay. No. Correctness is clear. Okay. And it is one of the arguably one of the most important signature schemes for RSA actually. It appears in a number of standard bodies and is actually used in practice. I have to say, actually, it's used in a slight variation because the hash functions used in practice, they don't magically output an element in the end. You have to do some other tricks, so that's actually not what's really used in practice, but let's, for the moment, suppose that is the scheme that's used in practice. Okay, so the other property that is actually interesting and remarking is that it's, first of all, signing is deterministic, which is nice because if you look, what goes wrong in practice very often is that randomness that is used, in particular during signing, which is a time-sensitive operation, randomness that is used is not really so random as the theoretical people would like it to have. Okay, so this one is deterministic. So I mean, there's no randomness, which is good. So one source of mistakes is gone. Okay, and the signatures are unique in the sense that if you fix a public key and a message, there exists exactly one bit string s such that the verification routine outputs 1. Okay, unique signatures, important. Okay, third pillar, the hard problem, RSA problem. I'm not going to say much about it. RSA problem is TA epsilon a hard to invert if all adversaries A running in time when it was TA, the probability that the adversary, it gets its input n equals b2, e and x, outputs x to the 1 over e, is bounded by epsilon a. Okay, so that's the concrete security definition of the hardness of inverting the RSA problem. Okay, now we can look at some results for security of this RSA full domain hash scheme. Okay, now the fourth pillar is security reduction. Now I'm giving the security reduction of Courant, which actually improves the original security reduction by Villar-Rogaway, 96. Okay, so it goes as follows. So assume the RSA problem is TA epsilon a hard to invert. Fix that. Then RSA full domain hash is TF epsilon f QS QH secure in the random market model. And now comes the interesting part where epsilon f is of QS times epsilon a. So it means in the security reduction we actually lose a factor of QS. Okay? So the reduction is not tight. It has a security loss of QS. QS is the number of signing queries, which may be large, of course, no? Because it's a signature scheme, and maybe we can establish during the life of the signature lifespan of a public key of a signature scheme a couple of million, billion signatures. So QS may be large, 2 to the 30. Okay, and then you can look at practical security, and then we consider the tightness of the reduction. So what we actually want is we want 80 bits of security, okay, for RSA full domain hash. So actually, for me, when I first thought about it, it was not really clear what it means. 80 bits of, for example, 80. It could be 128 bits or whatever you want. What does it exactly mean to be 80 bits of security? And the reasonable definition that came up is that for every adversary f against RSA full domain hash, the work factor, which is the difference, the quotient between the time the adversary spends on attacking the system divided by the success probability, should be at least 2 to the 80. Okay, so that's my definition of 80-bit security, which I think makes sense if you think about it for a moment. Okay? Okay. So the work factor of this adversary should be at least 2 to the 80, which is defined by TF divided by E epsilon f. Okay, so if I say for if the adversary can make, say, 2 to the 30 signing queries, which seems feasible for 80-bit securities. Okay, on the other hand, if you look now at the theorem, you plug in the values, that requires that we actually need a hardness of RSA against all adversaries A with the work factor, which is attacking the RSA problem, TA divided by epsilon A, and you plug that in, this is QS TF divided by epsilon F. And then actually we lose, since we lose this 2 to the QS is 2 to the 30, we need actually that the RSA problem has to be hard against the adversary with the work factor at least to the 1 or 10. Okay? So since RSA, there is a sub-exponential attack against RSA, this screws up our modulus size. So what we actually need in practice, right? This is the practical security. We need actually a bit size of at least 2,000 bits. If the security reduction was tight, we only would need 1,000 bits. Okay, so we lose something. So in order to compensate that, we have to choose the modulus n much bigger, such that the RSA problem gets much harder to attack, and particularly it's even hard to attack against adversaries that have, say, 1 or 10 bits of resources. Okay, so that's, I guess, this is all stuff that you know. Okay, so what does it actually mean for RSA full domain hash? So there's one side, there's the theory. People that would say, all right, so we should use RSA full domain hash with a large modulus, 2,000 bits or more. So then we actually know our security reduction actually gives us that full domain hash is as hard as making RSA or factoring n with 1,000 bits, which we hope it's secure for the moment. Okay? Of course, practice people say, I mean, you're stupid, you're not going to use the RSA full domain hash with 2,000 bits. I'm just going to use RSA full domain hash with 1,000 bits because otherwise it's getting way too inefficient. Okay, so that means full domain hash is as hard as as breaking RSA factoring. That's all what our theorem tells us with only 500 bits, which we of course, we know that this is easy. Okay, so our theorem is actually doesn't give us anything anymore. Or the other thing that people could use in practice is that, okay, so we don't have a tight security proof for full domain hash. I care about theory, I take that serious. So I use a different scheme. I use RSA PSS, probabilistic signature scheme. which is probabilistic. Okay, so it adds some randomness during the signing process. But then, the whole idea of going with this scheme in '96 was actually to get a tight security proof. Okay, so in order not to have an RSA modulus of 2,000 bits. Okay, so that's the two options. Okay, of course we can ask ourselves now, and now again the theory people, yeah, Peter Chuck?
Why is randomness a problem with signatures? I know it's PRF.
Yeah, I mean, of course you could use a PRF, yeah, that would make your life easier. Yeah. Yeah. Anyway, then you would have to evaluate the PRF, which would make things at least less efficient, okay? And we should always go, if it's possible, we should always go for simplicity. No, but yeah, you have a point. Okay, and then people thought, okay, we don't want that. We want actually a tight security proof for full domain hash. And then exactly 10 years ago, Coron came up with the following result, which is negative result. Which for me, it was at Eurocrypt 2002, and it was my first Eurocrypt. So for me, it was this is a great result, and it's still a great result. Okay, so this is the theorem, a little bit informal. So if there exists a reduction from the security of RSA full domain hash to the hardness of RSA that is loses a factor that is smaller than QS, a tight one if you want, then this reduction actually can be used to break RSA. Okay? So of course that means such a tight reduction cannot exist. Okay? So what I want to do now is I want to show you the proof on the blackboard. And I want to ask the tech person to raise this thing. Oh, he does. Okay. Magic. Okay. So how does that work? So what does the theorem tell us? Okay. So first of all, we have a reduction here. There's a reduction here. Reduction R. So what is a reduction R? So I want to reduce the security of full domain hash to RSA. So what is a reduction input some n, some e, and some x, and it would like to output some x to the e, say, it would like to output some x. Okay, that's a reduction. And it does that, the reduction does that by interacting with a forger. So let's say it is a epsilon f, tf, qs, QH, forger, it's called forger capital F. Okay, he does that. Okay, so how does it work? It gives, the reduction gives the forger a public key. Say it's N and E, okay? All right, gives that a public key. And then it, it sort of interacts, and the reduction sort of has to simulate the signing queries, the random marking queries, and then in the end, sort of the, make it like bitter here, I guess. No? In the end, the forgery outputs a pair of messages, M star and a signature star. And if that one is valid, from this forgery, the reduction can actually output the X. So that's the reduction, okay? And it does that and with probability epsilon R. Okay. So now we want to abuse this reduction here in order to break our own RSA challenge. Let's do that. Okay, so now we are the inverter I. Okay, I think you were first.
Okay, so does the reduction have to run the forger with the same n?
Yeah, hold your thought. That's going to be important. Is that the same?
The same question.
Same question. Yeah, it's okay. So
what was the question? I didn't hear it.
Oh, the question was, does the reduction have to run the forger with its same n or not? And I said, hold your horses. Okay? I'm just repeating what Caen said in 2002. Okay, all right. Let's try to build the inverter. Okay? So we are the inverter. Okay, inverter. So that's the RSA inverter, capital I inverter. Okay. Okay. So what we have to do now is, given us this reduction, this is given. Okay. So what we have to do now, we have to simulate a forger. Okay. you have to simulate a forger. Let's call it fsim. Okay, such that the reduction actually thinks it's interacting with a with a real forger. Okay, and then in the end we have to provide m star sigma star, and then the reduction will give us as output the x, which we can use as our solution to the RSA problem. Okay, now I'm giving you a simulation of a forger. Okay, so I'm simplifying the result a little bit, but here it doesn't really matter. Okay, let's first fix some universe M, which is some sort of signature queries or hash queries that we're going to make, and these are just, let's assume that the messages are just 1 to QH. Okay, so let's assume that those are in the message space somehow. Okay, let's fix that. So then we take set of signing queries. It's 1 unto QS, and they're all randomly chosen from M here, from the universe. Okay, somehow, no? Okay. Let's assume that. And then we take another message M star, which is somehow chosen, from M set minus Q. Okay? So this M star is not contained in this signing query. Okay? Okay, what we're going to do now? So now we're going to ask this reduction here. Okay? Right, we're still interacting with the reduction, no? Reduction is giving us the public key. Now we have to make some hash queries or signing queries or whatever we want. You have to make QH hash queries and QS signing queries in order to be a proper epsilon FTF QS QH forger. Okay, so we're just going to ask the reduction to hash us the set of messages M, and it gives us back hash of M. Okay, that's our first step. And the second step, we're just going to ask sign us the message M star. Okay, so second is just send M star, and you get back sigma star is sign of M star. Okay, so now we're doing something. We rewind the reduction here to an earlier state. So we ask this query here M star. Now we rewind the whole reduction, which of course we can do because we provide the randomness reduction. So we go again with the same randomness until the hash query is here, right? Say until here star. So 2 prime is rewind to star. Okay, and then we make a different set of signing queries. Okay. So now we actually behave like a proper QS forger. So we ask for the messages in the set Q somehow, and get back a set S which contains sigma 1 until Q sigma QS or sigma QS, which are the signatures. Okay, so ask the message set Q. Okay, good. Okay, what we do now, and now it looks a little bit like cheating actually, but it works. What we do now is we actually can send M star and sigma star as our forgery. So why is that? My claim is that now this is actually valid forgery. Why is that a valid forgery? Because, okay, so after the rewind, the reduction, it has no clue what happened before the rewind, right? So 2 doesn't exist anymore, so it's 1, 2 prime, right? So we first make QH hash queries, then we make the QS signature queries, right? Q, set Q, the Q doesn't contain this element M star, okay? So, but still from after the rewind, we have this M, the sigma star, you know it, okay? So we can provide it as a signature, okay? Looks like cheating, but somehow it magically works, and there's the question.
Why does the reduction has to supply you with signatures?
Because it's a reduction. That's what a reduction. That's the definition of a reduction. So a reduction interacts with the forger and has to simulate a view of a forger. In particular, it has to output the signatures, to simulate the signatures, and then use the forgery somehow to break the hard problem. Yeah?
So, when did you use the structure of full domain hash?
Yeah, it's a good question. I haven't used it. It works for any unique signatures, the argument. So I'm not using anything of full domain hash. Was that also your question?
Is it clear that you can extract X from M star sigma star?
Well, again, that's the definition of the reduction. It's
Yeah,
a reduction, so it
just
has
said-
to do it by definition. If it interacts with a valid forger, I mean, not that this is a simulate forger. I have to show you that this is actually somewhat close to a valid forger. Okay? But if this was a valid forger, a real forger, then it has to output the X with a certain probability. That's the definition of a reduction. Okay? Oh, another question.
This is a stupid question.
Yeah.
So where does the tightness come into the picture? Where does
I'm not finished yet. I'm not even finished with the definition of this inverter. Okay, now we have actually, you do another, so actually we have, I'm coming back to that in a second. Okay, so we have to simulate an epsilon f forger. So a forger that outputs a valid signature with a probability epsilon f. So actually we have to, in the third step, we actually have to fail with a probability 1 minus epsilon f. Yeah? And then else only submit the forgery. Only if you don't fail. That's in order to be actually a good epsilon f forger that outputs the forger with the probability epsilon f. Okay. All right. So let's continue the argument of Paul. That completes the description of the forger. Okay. So now I have to show you what is the probability that this inverter actually works. Okay. So this is by definition, this is a reduction. So we know that if the reduction interacts with a real forger, a perfect forger, a real epsilon f tf qs qh forger, then it has to output the x solve our problem with probability epsilon r. Okay, so we.
As a fact, I mean, ignoring the note's initial question, what if the reduction talks to multiple attackers, has a lot of attackers concurrently? So
Yeah, that's also a good question. So let's assume we have only one
That's
attacker.
What assumes? He assumes there's only
You can
one.
you can generalize it to sequential attackers.
Oh, I see. So there is a problem if you start.
Yeah, parallel. Yeah. Parallel is a problem. It's an open problem. I don't know how to solve that. Okay. All right. So so now we make a thought experiment. So let f real be a real forger. So let f. So that is our simulated forger. So now we define f real be a real forger. So who makes the same queries? Who makes same queries? Q and outputs a forgery. Let's call it maybe sigma star real on m star. Okay, a thought experiment. So we know that by the definition of the reduction that the probability that if the reduction interacts with its real forger, okay, I write f real, reduction inputs n e and x to the e, that it outputs x, okay, so that is epsilon r. That's by definition. Okay. The second thing that we know is that the probability that the reduction, when we run it with our simulated forger here, okay, and ex to the e, that it outputs x, that is the probability that our inverter succeeds, is epsilon I. And of course, the question is, what is the difference between these two things, no? Let's look at the difference, the probability again that, okay, so r f real, something outputs x minus the probability that r interacting with f sim outputs x. Okay, so what's the difference between these two things, these two games? Okay, so actually what can go wrong between these real and this inverted forgers? Okay, so the first of all, the argument is that since the RSA, now comes the important argument of Courant, since the signatures of full domain hash are unique, means for each bit string there exists only one signature, exactly one signature. Okay? So that means that the real forger, the sigma star real of the real forger, has to be the same always of this one here, that the reduction outputs here. Okay? That means we can, this is actually a valid forgery and the reduction can later use it. Unless something goes, let me finish the argument and then come back to you. Unless something goes wrong, and actually what could go wrong is that, okay, first of all, so the bad case is that this sigma star is not correct here, but then the rest of the answers are correct, meaning that the S was answered correctly, all these queries are correctly, so this is incorrect, but these are correct, but the fail doesn't happen here. So that's the difference between these two things. Explain it one more time later. So that's smaller than, equal than the probability that sigma star is incorrect, right? Because then the forgery is not correct, that the simulated forger outputs. And so all these S is correct. That means the forger actually gets the right answers here, and so it has to output a forgery here. It could be lucky that, the only of the answers is wrong, and say, okay, I'm not talking to a right experiment, so I can just output fail, okay? And S is correct, and fail doesn't happen, no? It could be lucky that all S is correct, this is incorrect, and then maybe fail happens, and then, the simulated, the inverter could be lucky, okay? So these are sort of the bad events, okay? Come back to you in a second, I just want to finish this argument, and then there's, okay, the probability that fail doesn't happen is epsilon f, okay? And then Courant showed by a combinatorial argument, which is correct, that this is more or less smaller equal epsilon f divided by qs, okay? So that part from here, take it as granted I want to go to this combinatorial argument, okay? So in total that we have then, now we need another blackboard, I'll just write it here. So in total, to finish up the argument, we need that epsilon I, the inverter, is greater or equal to epsilon r minus epsilon f divided by qs, more or less. That means that inverter probability gets positive if this, reduction here doesn't lose more than a factor of qs, because then this one gets positive, and then we can use this inverter somehow. Okay? Okay, so now, sorry, Mina. Yeah.
So you're using the fact that this is a really unique signature,
Yeah.
since there exists only one signature, as
Yeah.
opposed to what you get from a PRF,
Yeah.
right?
Oh, what?
As opposed to what you get from a PRF, right? You can take any
Yeah.
randomized signature scheme, like Christoph said.
No, so there's a difference between a randomized signature scheme and a unique signature scheme.
So you're using the fact that it's
A non-randomized, a deterministic signature scheme could have non-unique signatures, no? Yeah? Or just append a bit and then ignore the bit in the verification. No, here it's important that it's unique. Okay. Okay.
But should also work for re-randomizing.
A re-randomizable signature scheme in particular has not unique signatures,
Yeah, right. But
so the argument wouldn't hold.
Yeah, but you could replace it by re-randomizing the signatures, and then the distribution of the signatures would be fine too.
But then the argument wouldn't hold anymore, because you cannot. I wouldn't see how it would work.
Basically, you would have an equivalence class of signatures if they're re-randomizable. So the equivalence class is kind of the signature.
Okay. I don't know.
Yeah.
Okay. Okay. So actually, I want to now convince you that the argument fails if the signatures are not unique anymore. Okay. And the argument actually fails because we cannot make this. This equation doesn't work anymore, because the reduction could need a different a signature in order to compute the x than it got provided here. Since the signature is not unique anymore, at first it could provide some other signature, but then the signature that it gets here wouldn't be useful for the signature, for the reduction anymore. Okay. I don't want to go much into detail here, but I mean, if the signature is not unique anymore, I think this argument doesn't go through anymore. Okay. So now, I claim there's a small, subtle flaw in this argument here, and it goes back to the two simultaneous questions in the beginning. And somehow Courant silently assumed that the public key, that the reduction output is actually NE. And of course, why do we have? Why does it have to be the case? Why does the reduction have to output NE and not something else? And that's actually the problem here. Okay? And this is where it goes wrong, really. Okay.
So you think that maybe you can prove it under like Phi hiding assumption or something?
All right. Hold your horses one more time. Okay. So the way to fix it actually is if now the reduction outputs some other, say, n prime E prime here, and now somehow the simulator here or the inverter would be able to verify if this actually defines the permutation, that the RSA function with respect to this n prime epsilon prime defines the permutation. In other words, with respect to this public key, the signature scheme still has unique signatures. Then we're in good shape, because then we can make this argument: this sigma star is the same, as the sigma star real that the start experiment adversary would output. Okay, and that's actually what we can prove. And now I'm gonna switch back to laptop again, to the slides again. So maybe we can lower the board again.
Magic one.
Magic. Ah, awesome. Thanks. Okay. First, I give a definition, and the RSA function is defined to be certified if given an NE, which may be any bit string. It can publicly verify that the RSA function is a permutation of our Zn or Zn star, whatever you want. And this is actually equivalent to, deciding is the GCD of E and phi of n equals 1 or not. Okay. And then the theorem that Sakikaki and myself proved is the same as Courant, but now the reduction reduces security of RSA fulmination to the hardness of certified RSA. So if RSA is certified, then it actually works. You can salvage the result. Okay. Question is RSA certified or not? Okay. For which parameters is this RSA problem certified or not? Let's look at the folklore. So if E is a prime and it's greater than n, then RSA is certified, of course. No, you just have to check if E is a prime or not. And then, since if E is greater than n, E cannot divide phi of n. It's not possible. It's always certified. That's easy. It's folklore. Okay. Next question is if E is somehow between n to the 1/4 and n, there was an open problem. I mean, from the work we had, and we very recently able to solve that with Sakikapi and Alex Mai. We actually can give a certification routine which is quite efficient. Square routine. More efficient than actually doing one exponentiation. But the interesting case is actually low exponent RSA. So if n equals to q and the exponent is smaller than 1/4, and they say E is a prime, okay? But actually RSA is not certified. So the Courant impossibility result doesn't hold anymore. Okay? You cannot salvage it. So why is RSA not certified? Because RSA is lossy. Lossy is in some sense the opposite of being certified. Okay? Let me remind you what is lossiness, what is a loss chapter permutation or function by Eike and Boris from 08. So the RSA chapter function is lossy if there exists an alternative RSA key generation algorithm that outputs some n prime e prime, such that, first of all, this is indistinguishable from the real RSA key. Okay? And then second, the RSA function plugged in with these parameters is not a permutation anymore. Okay? So again, since this is indistinguishable, there exists an alternative key generation, it cannot be certified. It cannot exist such a, no, it's the opposite thing of being certified. Which
This is based on an assumption.
One second. I should say that this certified is actually something which was introduced by Bellari and Wang. The definition of being certified is a something that was introduced by Valery Young in also more than 1 decade ago. I have to say that. Okay, so why is RSA lossy? And give you the alternative key generation algorithm. It just outputs n prime and e prime, such that e prime divides phi of n prime. And then, of course, once we have that, then the RSA function is e prime to 1. So it's lossy. It's not certified anymore. And exactly these two things, these two distributions here, you cannot distinguish between assuming the phi hiding assumption. This is exactly the phi hiding assumption. Okay, now it gives an concrete RSA key generation algorithm such that these two things are indistinguishable. It's sort of an old assumption. It's was composed by Kamenisch, Mikali, and Stadler in 99, and it's in particular is wrong for if the e is too big, because you can see that you have some knowledge about the e, which it divides phi of n, right? So if the e gets too big, then you have too much information about phi of n, so you can use Coppersmith in order to factor. Then the phi hiding assumption gets wrong. Okay. There's a this is more or less a tautology that the RSA function is lossy under the phi hiding assumption and the right parameters. Okay, so now that we know that the RSA function is not certified for small e, maybe we can use that, and we can actually do that. We get a tight security direction for RSA full domain hash. It's something that my student Saki Kapi will present next week at Eurocrypt. So I'm not going to go into detail here, but if we assume that the RSA function is lossy, so say under the phi hiding assumption, then there is a tight security proof for RSA full domain hash. It just uses a factor of 2. The proof is actually quite simple, but we'll see it next week. So what does it mean for practical security? So the best attack against the phi hiding assumption is actually factoring. So it means if you go back to the tight computation of this tight security bounds, then you can see since you have this tight reduction, believing that the phi hiding assumption, which is of course a stronger assumption than factoring, is the same as factoring, then we can still use an RSA modulus of small size 1000 bits. And if you want concrete security, so if you take the original proof by Balararogi, where you lost a factor of QH, then you would need a RSA modulus of 3000 bits. This value is a little bit arbitrary, but okay. Courant 2 to the 30 lost, so you need 2000 bits, and for the new tight proof, you need only 1000 bits. And of course, what is now open is still the tight security reduction to RSA, because this is only the phi hiding assumption, which is much stronger and should be taken with a little bit of salt. Okay, so we don't know about that. Okay. So I think that was all I wanted to say about the security of full domain hash in the random oracle model. Now let's move on to the standard model. I only have 50 minutes left, so I have to rush a little bit through the results in the standard model. Okay, so what I'm going to show you is first an impossibility result. Okay, it's actually not possible to prove anything here in the standard model, and then also contradicting a bit, but there are some possibility results. So in order to, first of all, you can actually prove that RSA full domain hash is a m-time signature scheme. Okay, for small m, fixed m. The size of the public key will grow in m, but still something. So we can weaken the model, still prove something. And then, once we want to have full security, then we actually have to tweak the scheme. So we have to use randomized RSA full domain hash. Okay. And there's a toolbox. So I'm gonna show you to you anyway. I don't have much time. I'm gonna show it to you anyway. I'm going to show you what are programmer hash functions. This is the central toolbox in order to get all these standard model security results. Okay, so first let's start with the impossibility result by in 2 papers. Both are Dodis et al. The et al. Changed over the years, I believe. No? Okay, so one is from 2005, Dodis, Olivier Peterchak, and the second one is Dodis, Dentes, and somebody. Heitner, exactly. Okay. It says more or less informally if F is a homomorphic, that's the new result from 2012 more or less, chapter permutation, then there exists no black box security reduction from security of F full domain hash, that's full domain hash with chapter permutation, to any non-interactive hard problem of F. So that's very informal. I don't want to describe it. much more, and essentially it says there is no security of full domain hash in the standard model, period, in the black box sense. Okay. All reductions are black box. Okay, what can we do? So let's try to prove something. And I'm going to show you, maybe in 5 minutes, in my eyes, it's an important tool to get all these positive results in the standard model. This is programmable hash functions. Okay. So what is programmable hash function? It's an abstract algebraic hash function. Okay. So think of it as a normal hash function. So it has a key generation algorithm that outputs a public description of the hash function, and then the corresponding hash function that takes k-bit strings, and it's an algebraic hash function. It hashes into groups. K-bit strings into groups. Okay, so that's nothing special. Now comes the special part. So we also need an alternative trapdoor generation algorithm that inputs two group elements, G and H, and outputs a public key, pub prime, and a trapdoor. Okay, so we need, in terms of security, that this public key is indistinguishable from public key, from the real public key of description. Okay, but we have this trapdoor thing now. And this trapdoor thing gives us actually something interesting, some sort of algebraic description of the hash function. It gives us a decomposition together with the trapdoor. So we can input the string x here and the trapdoor in our trapdoor algorithm, and then we output the red a of x and the blue b of x, and it gives us a decomposition of the hash value. So the hash value can be written as g to the h of x times h to the b of x. We call that these G and H are the generators we put in the trapdoor, and they're arbitrary. Okay, so we get some sort of decomposition here. Okay, that's trivial to achieve. And now comes the non-trivial part, the so-called M and N programmability. These are, let's think of it, small integer values. Okay, M and N. Okay, but it sort of resembles some sort of random oracle functionality in a real-world hash function. Okay, all right, so now this is a little bit difficult to parse. I try to explain to you. So we need that for all public keys, pub prime, that come out of the trapdoor generation algorithms, for all bit strings, x1, xm, so this m here, for all bit strings y1 until yn, this n here, okay? They have to be pairwise distinct, x's from the y's. Okay, now comes the difficult part. So the probability space in a second, the probability that these b values, they're all 0, and the b values of the x values are all 0, and the b values of the y, the green and the blue y values are all non-equal 0. The probability has to be non-negligible, or noticeable. Okay, so what is the probability space? So we fix the pub prime and we run over all different trapdoors that are output by the trapdoor generation algorithm. Okay? So what does it mean? So once we have that, so we can sort of bet on that this event happens with a good probability here. So once this happens, we can plug in this decomposition again, and we know that for all these red xi's, the hash function actually evaluates to just g to something, which we know. And for all the blue yi's, we know that the hash value decomposes to g to something times h. So this has an h component, and this doesn't, with a good probability for all bit strings. Think of signature schemes. So these are somehow, some messages and some other messages, and somehow the hash function behaves differently. This is also the way the full domain hash original full domain hash signature proof works. And somehow we can do something, and with some we can't. So partition. Somehow we can maybe solve, or we can simulate the forgeries, the signatures, and with some messages we can't. That's the general idea. Okay? Okay. So there is a construction of an M1 program hash function that I'm not going to show you. Essentially, the important thing is that it uses cover-free maps, and it has a public key size of, so M1 program hash function has public key size of M squared times the security parameter, the input length of the hash function. Okay? And it's a nice and interesting problem to get a M1 program hash function with better security parameters. Have a big impact on many standard model schemes. Okay. So let's look at RSA full domain hash. There's a theorem that says that assume that H is an M1 program hash function and RSA is hard to invert, then RSA full domain hash is an M times signature, meaning that the adversary can query M signatures, maximal M signatures, the M from the program hash function, then he has to submit a forgery. Not polynomially, just n. Okay? Okay, so how does it work? How does the reduction work? So the RSA reduction, just in a nutshell. The RSA reduction inputs n, x, and e, and wants to compute x to the 1 over e. So that's its goal. Okay, and all right, so we run this funny trapdoor generation algorithm, and now we run it on two generators of the group. The one is x to the e, and the one is x. Okay, e from the RSA challenge, and this gives us the public key and the trapdoor. And now, okay, so now comes the important equation. Now let's look how signatures, full domain hash signatures, look like. A signature on a message m is hash of m to the 1 over e. Okay, so we plug in the decomposition of hash of m, which is g to the a of m times h to the b of m to the 1 over e. Done that. Okay, so now we plug in, so we know that g equals x to the e and the h equals x. So this is x to the e times a of m, x to the b of m to the 1 over e. So you see that this 1 over e cancels out. So this is x to the a of m times x to the 1 over e times b of m. Okay, so this is how a valid signature looked like. Okay, now the observation is that the simulation of a signature is possible if and only if this b value disappears, because that's the x to the 1 over e, that's the one that we want to compute in the simulation. So that's the one we don't have. So this disappears if b of m equals 0, of course. And then we can simulate a signing query, because it's independent of the secret key and more. On the other hand, if b of n doesn't equal 0, then this signature somehow contains this x to the 1 over e component that we're actually looking for. Okay, so that's the one that we can use to break our hard problem.
What if b of m is 0 modulo e? I mean, what if b of m is equal to e, for example? That's also a problem.
What?
What if b of m is equal to e, to the exponent t?
Oh, okay, I mean, then oversimplifying things here. You have to, in reality, this is much more difficult. You have to make sure that all these weird cases don't, yeah. And they're also not independent and nothing, so oversimplifying a lot. Okay? So let's say M1 and until MM are the signature queries and M star is the forgery. The only thing we have to make sure is that the probability that all these b values of the red, of the signing queries, signature queries are 0, because then we can simulate. And the b of the blue value of the forgeries doesn't equal 0, because then we can use it to break our hard problem. But wait a minute, this is exactly the definition of this program hash function. For all strings, it's that, particularly for the one that address the outputs. Yeah, we know that the probability that this actually happens is non-negligible. Suppose this happens, then we're in good shape. They can simulate, and then we can solve the RSA problem. And that's the whole sort of spirit of all these program hash functions. Okay, so that's the spirit of the proof, and that means we can plug in this program hash function, and then we can instantiate it. Okay. There's the caveat is, or the drawback is that this program hash function has the last description of the public key, which also means it doesn't contradict the impossibility result of Evgeny et al. Okay. So maybe just one slide about the randomized RSA full domain hash signatures. How does that work? Okay, so we are stuck with the impossibility results. We cannot prove anything about full domain hash, except maybe m times signatures. Okay, so you have to change the scheme. Okay, and how does that work? So we do a randomized RSA full domain hash. The public key is some n, and then now we need two hash functions. One is a program hash function, and one is some other hash function specified. But they're all non-random arc. They're all real hash functions. You can give you the description. It's all real stuff. Okay. So how does signing work? It's not probabilistic. So it picks a random r from 0, 1 to the t. Okay. So random salt, and then computes the signature or the s as hash to the m to the 1 over p of r. Okay. So p is some mapping that maps the random string into something else. Okay, and that's all. So instead of having a fixed exponent, we make the exponent depend on the randomness that we pick. Okay. The verify does the obvious thing. Okay. What is these hash functions? The hash function p is some. I want to specify it any further, but it's some mapping goes to 0, 1 to the t into some primes. If you want the reduction from the strong RSA assumption or the product of k primes, the Homburger-Waters technique, you can then do reduction with respect to the RSA problem. Okay, don't want to go much into details. H is a M1 programmer hash function, and the interesting thing is actually that the value of M here, it controls the length of the randomness. So the greater the M is, the smaller is the randomness. The smaller can choose the randomness. Okay, and that is done by this equation here. This is the number of signature queries, security the parameter divided by M. So if M is say 8, no, then you have say log QS 30 plus 80 divided by 8, it's 10, it's 40. Okay, that's enough. Okay, maybe one line about again how you prove that. Again, very rough proof. Okay, so the theorem is assume the RSA function is hard to invert, and H is a program hash function. I don't specify P any further. Then RSA randomized full domain hash is secure. It's also not a concrete reduction because it's not tight. It's also complicated. Depends on this program hash function, this P. Okay, so suppose that R1 until RQS is the randomness used in designing queries, and R is the randomness of the forgery. Okay, then we can distinguish between two cases. So first, the randomness is recycled by the adversary. So R star is in R1 until RQS. That's an interesting case. And the other case is R star is sort of fresh. Let's look at the interesting case that R star is in R1 until RQS. Okay. So again, now we want to build an RSA reduction. A reduction that inputs n, x, and e, and wants to compute x to the 1 over e. Oh no. So what we do now is that we pick R1 until RQS such that with high probability there are no m plus 1 collisions. M is again the parameter of the program hash function. Okay. So why is that? Or what does that mean? This actually has implications on the length of the randomness here. So you want that with high probability that there are no m plus 1 collisions. By the expanded birthday paradox, it means that we can have to choose Ri, can work out the formula. This is the formula that we get. Okay, so we just want to make sure that we don't have m plus 1 collisions, but we may have m collisions here. Right? You can think that if you maybe choose R equals 10, if you choose all these random, then you have lots of collisions. No? So you have to choose R sufficient large that you don't have m plus 1 collisions. Okay? So in the worst case, say we have R star is Ri1 until Rim for some indices I1 until Im. Okay. And now we want to set up this chapter generation algorithm, again, leaving out many details, such that the simulation of the signature queries here is possible if and only if either B of Mi, so the H value disappears in the decomposition, or the randomness is not one of these randomnesses here. Okay, and these two cases you can simulate. In all other cases, the signature somehow contains the value that they're looking for. Okay, and this is again where the programmer hash functions come into the game. So somehow we have to simulate the signature queries for all these Ri values that are equal to this R star value. Okay, and this is again what the programmer hash function gives you. The probability that for all bit strings that all these m values are 0, and all the blue values are non-equal, is non-negligible, and then you're done with the proof. Okay. Essentially, what I wanted to tell you is, first of all, you can use the program hash functions again here, and there are sort of the idea is to take care of these collisions in the R values here in the randomness that you cannot avoid because you're going to take the R as small as possible. Okay. Okay. All right. And that's all I wanted to say about full domain hash and the RSA full domain hash signatures. I'll just go to my summary. It's exactly 11 o'clock. So RSA full domain hash first is secure in the random oracle model. There's a non-tight security reduction from RSA to RSA. Previous thought that there doesn't exist any tight security reduction at all, but now we saw that the proof had a small and subtle flaw in it, and we could exploit this flaw by showing a tight security reduction to a strong assumption, the phi hiding assumption. Unfortunately, if you move over to the standard model, you can see that RSA full domain hash is provably unprovable. Okay, there's this black box impossibility result, but again, we can escape this result by either going into a weaker model that we show that m time signatures, that RSA is secure as an m time signature. But again, the public key size grows quadratically in M, which is not what you want, of course. Or we could sort of tweak the scheme and then have a randomized version of RSA full domain hash, because people probably wouldn't use in practice. But anyway, this is as far as we get. And that's all I wanted to say. Oh yeah, and OIP and DSA, I could do a similar talk, and they have similar results. OIP, we could also have some sort of standard model instantiations, but it doesn't really work. And with DSA, even less is known. And that concludes my talk. Nigel was first.
You say you've got some results for DSA, but any results for DSA are interesting because there isn't, apart from in the generic group model, there is no proof.
Yeah, that's what we thought. We thought we had this great result, but then we looked up in a talk by who is that? Dan Brown, and he actually showed something quite interesting. He doesn't really make it formal, but in his own language, he proves that these
signatures in a UFCMA experiment are as secure in the random oracle model as in a unfortunately against no message attacks. Okay, so they're as secure if you give the adversary many messages. They're as secure as if you don't give any signatures to the adversary. And this is as far as we can go in the random oracle model, at least. Yeah. Which I didn't know about this result, and I think it's a great result, but it's somehow hidden.
That's just because the thing's like the underlying Sigma protocol is simulatable, yeah. So that's essentially.
Yeah. I mean, there's a reason why it seems hard, but it's not inherent. So maybe we can do something about that. That's an interesting open problem. So then there was Yevgeny was next, I think.
So your pi hiding result, does it extend to general lossy TDP?
Yeah, exactly. Yeah.
Oh, for all lossy TDPs, you don't need homomorphism at all.
No, we don't need homomorphic. It also extends to PASS. You will see next week at Eurogroup. Yeah.
You want to use this phi hiding assumption to set key sizes, right? You have this table where you say, I want to still use 1000-bit keys. I guess you can only do that if you assume that the phi hiding assumption is exactly as hard as factoring.
Yeah, that's what I assumed. That's what I said also in the slides.
But in practice, this is interesting because almost every RSA public key, E, is 2 to the 16 plus 1.
Yeah, exactly. Yeah. Or 3. Yeah. And for these, the phi hiding assumption could hold.
Yeah, exactly.
And we cannot break it. That was our motivation, to look at low exponent RSA and see if we can get a precise. I didn't say that, no? It's a good remark.
Just maybe a very quick question. So the last result, randomizing, how is it different from GHR and also Hochenberger-Water signatures? I mean, they also
these
take
are all
different
special
routes.
cases of this more general framework.
Oh, I see.
I should have said that. This is a general framework, and particular cases for particular hash functions, Hochenberger-Waters or Gennaro Dahl and Fischlin, Kreimeshub, and all these things are all special cases of this general framework. I didn't specify neither P, neither H or anything, so that's why, I should have mentioned that. There are like tons of these schemes, and this all generalized this signature.
You said that p hiding holds up to like n to the 0.25, and above that it's also certifiable. Is there like a gray zone where you can't say nothing, or what's the constant?
There's I think there's there's actually a gray zone, but the gray zone is if E is not prime, if E is composite, then there is a gray zone. So in the result that I gave you with if it's certified or not, I always assume that E is prime. So if E is large and it's sort of hard to factor, then we cannot say anything about it. We don't know if it's certified or not. But otherwise, there's no gray zone. I mean, somewhere there's this polynomial versus sub-exponential thing, then this gray zone exists. But other than that, it's sort of tight.
Into phi, it's like tight if you can.
Which direction?
Phi hiding to factoring. So you said phi hiding is a stronger assumption. So the other direction is obvious.
So if you can factor, you can break phi hiding, of course.
Yeah.
Yeah, I mean, if you can factor, you can compute phi fn, you can just test if E divides phi fn or not. But and also, yeah, it's philosophy.
So, okay, let's thank the speaker again.